In this tutorial, we will learn how to run a paired samples t-test using R. A paired samples t-test, sometimes called a dependent samples t-test or a repeated measures t-test, depending on how the data or structure what the data actually are, is a way that you can evaluate whether or not the difference between two vectors, the scores in two vectors, whether those differences are significantly different from zero on average. Okay, so in other words, we're interested whether or not the differences between two variables, which in this case are dependent on one another, if that average difference is significantly different than zero. Okay, so the first thing that we're going to do once we have RStudio open is go to File, New File, RScript, and just making a note up here using the hashtag paired samples t-test in R is what we're doing today. Let's make sure that we set our working directory. I'm going to move quickly through this, but if you have any questions, check out the other tutorials that are on setting your working directory, as well as what we'll do after that, which is reading data into R. So I'm going to use the setwd function, and with quotation marks here within the function as the sole argument, I'm going to specify the exact pathway for my working directory folder, which is where the data live for this data exercise, or where I've saved the data for this exercise. And so this way I'll be able to quickly read in the data. Mine is my H drive R workshop folder here. So I'll hover my cursor somewhere on that line and click run. Now, alternatively, I could have done session, set working directory, and choose directory to do drop-down menus to access that. Now, the next thing that I'm going to do is read data into R here. And I'm going to use the read_CSV function, which comes from the reader package, which is part of the tidyverse package of functions, which means we need to actually install that package if we haven't already, and at the very least access that package if we've already installed it previously. So if you have never installed or you have not recently installed the reader package, it's reader with all lowercase and no e. Make sure that you install it. I've recently installed it, so I won't do that here, but do make sure you put the double quotes or put the quotation marks around the name of the package there when you use the install.packages function. I am, however, and at the very least you need to do this, use the library function, assuming you've already installed this package at some point, and put the exact package name in the parentheses as a sole argument, and then click run when your cursor is somewhere on that line. And so here we see in blue that it seems to be successful, meaning we do apparently have that reader package installed and we have now accessed it so we can use the functions. Now we're going to use that read_CSV function from the reader package, and we need to come up with some kind of name for this DataFrame object. I'm arbitrarily going to call it train D because this is we're going to be working with training data. In this case, we're going to try to evaluate a pre-test, post-test without control group or with no control group design. And I'll use the left-handed arrow here to say this is what I'm naming this new data frame object that I'm about to read in. And so where are the data coming from? Well, I'm using read_CSV here, the name of the function from that reader package, and in quotation marks as the sole argument within the read_CSV function, I'm going to type in the exact name of the data file. So what is the name of the data file that's located in our working directory? Well, I'll go to that working directory folder. This is my working directory folder. Yours is likely different. And I am going to click on the exact name of the file, which is this case, training evaluation _ pre-post only. I'm going to copy that exact name, go back to RStudio, paste that exact name into the quotation marks there, and make sure that I add a .csv if it's not already there to tell the function that this is indeed a .csv or a comma separated values data file here, which it is. So let's go ahead and run that line of script there. And you'll see that now we have in our global environment the name of that new data frame object, which is train D, which is what we named it here. Let's click on the name there so we can view this data frame in our global environment. And so here's what I mean about this being a paired samples, or in other words, a dependent samples t-test that we're doing here. So you can see with each row in this data frame, we have a unique employee. So this is their unique employee identifier number here. And we have two variables, pre-test and post-test. And as you can see, every employee has scores on a pre-test and a post-test. So these scores are actually paired by the employees. So the same employee is receiving a pre-test score and a post-test score. And you can go down and see this throughout. And you can see that we have 25 different employees in this data frame here. Okay. So our question is if you were to look at the differences, so let's say post-test minus pre-test for each person. So for the first person, that would be a score of 23. So positive 23, that's the difference, meaning they increase their score from pre-test to post-test, in other words, from before to after training. Our question is, on average, those difference scores, are they significantly different from 0? Well, that's a question, assuming we meet the statistical assumptions that I'll outline in a second, that we can test using a paired samples t-test. So to that next point, let's do statistical assumptions and review what those are for a paired samples t-test. I'm just going to type these out for you as a note. So the first one would be that the difference scores, so you'll see what this means in a second, but I just kind of gave you a preview of what those difference scores are, that the difference scores are independent of each other. Now that might sound a little bit confusing because we're calling this a paired samples t-test or a dependent samples t-test, and you might be thinking, well, doesn't that mean that we'd want actually an independent samples t-test? Well, no. What we're saying is that these scores are, yes, they are indeed paired within the person, but we're saying each individual person is their difference score is independent. In other words, it's not nested. There's no nesting in the data with groups of employees and things like that, at least statistically speaking, that we're maybe oversampling or something like that, or that there's some kind of non-random sampling that's happening here, okay? And so another way of saying this is that essentially the cases, which in this case are employees, are randomly, I'll do a new line here, cases are randomly selected from the underlying population, okay? Now this is a challenging one to meet in some instances, or to defend rather, depending on what kind of data you have access to. But if you, in this case, we're going to assume that yes, there's no kind of bias or dependencies in the data here, that in fact, yeah, this is just a random assortment of people. And so let's assume in this case that we did randomly select people from the organization to participate in this pilot training program here, and we're using a pre-test, post-test without control group design, okay? So the second statistical assumption, that this is one that we're going to more deliberately and specifically test in this case, is that the difference scores are normally distributed in the underlying population, okay? Now, what does that mean? Well, that means that we're really looking for univariate normality here. So when we look at that distribution of difference scores across all the employees, that there's a more or less normal distribution, okay? All right, the next thing that we're going to do is we are going to look at the second statistical assumption, at least visually, to get an idea of what is the distribution of this particular difference score, set of difference scores we have. Okay, so to get an idea if we've met that second assumption of univariate normality in the distribution itself. Okay, and so to do that, test statistical assumption 2. To do that, we're going to first create that difference score variable so we can actually look at the distribution. So to create the new variable, we're going to type in the name of our data frame followed by $, and then we're going to create a new variable name. I'm going to call this diff for difference score, and it's just DIFF all lowercase, and I'll use that left-handed arrow to note that I'm naming this new variable here, which I'll use, and here you see the $, saying this is going to be attached to this existing data frame, which is the one that we read in a name called train D. So how do I compute this difference score? Well, this new variable, it's really quite simple. This is basic arithmetic here. So you'll just write out this equation or something like it. And that is type in the name of the data frame and then post-test. So the name of the variable that comes second in this case, because this is a repeated measurement, okay? And then minus. And then again, name of the data frame, which is train D, $, to say that the next variable belongs to that train D data frame as well, and that is pretest. So post-test minus pretest will equal our difference score variable. So watch what happens when we run this. Well, blue means everything's good. Let's take a look at our data frame object here again by going to our global environment. Now we have a fourth column here, which is a new variable, which is our diff variable we just created. And here you can see those difference scores. So this is an increase of 23 from pretest to post-test. So it's just post-test score minus pretest score for this employee, and then you move down the list and do it for each person. Now, a positive score in this case, by how we specified this, post-test minus pretest, means an increase from before to after training. whereas a negative would indicate a decrease in the score, in this assessment score from before to after training. Okay? All right, so now using this difference score variable, we're going to use a plot function, or the plot function from base R. So let's do install.packages. And if you haven't already, make sure that you've installed the lessR package with the capital R. Make sure that the lessR name of the package is in the quotation marks here. I recently updated this, installed this package, so I don't need to do this, but at the very least, I'm going to use the library function with lessR, the exact name of the package, in the parentheses here is the sole argument, because I need to access this package to use the plot function, and then we'll also use the t-test function and the bar chart function from it subsequently in this tutorial. So go ahead and click run. Okay, so now we're going to use that plot function from base R. And so what do we enter as the plot function as the first argument? Remember, this is plot with a capital P. Well, as the first argument, enter the name of that difference variable, or the variable we created above, which we call diff. So diff, all lowercase. That's your first argument, so add a comma. And then just data equals and specify the name of the data frame to which that new difference score variable belongs, which is train D. So let's go ahead and click run. Okay, and here you get a visual of what this distribution looks like. So this is the difference score. This is a VBS plot, violin, box, scatter plot. And so we get the violin, we get the box plot, and we get this univariate scatter here. This looks relatively normal here. We don't see any major skew in the data. And in fact, if you go to the output here for this variable, you'll see some descriptive information like the mean, the standard deviation, the interquartile range, which is between here. And then also you get the skew. And so the skew is actually, there's very little skew here. So we do have pretty good evidence, at least visually, and some statistical evidence that this looks to be a relatively normal distribution. Well, we'll actually do a more stringent test of that in just a moment, okay? In the t-test function itself. So let's now run paired samples t-test in R. And so there's different ways that you can do this. You could use the t.test function from base R, but it would require some additional steps. And in the written tutorial that corresponds to this video tutorial, you'll learn how to run a paired samples t-test if you choose to in using the t.test function from base R. In this case, we're going to use the t-test function, so t-test all lowercase, from lessR because it packs a lot into it. So as the first argument in the t-test function, let's enter the variable that comes first. At least in this case, it's chronologically, which would be the pretest. Now, this is really what you're specifying here is which variable do you want to be subtracted from the other one, okay? So in this case, we're saying subtract the pretest. So this is our first argument from the post-test variable. So post-test being our second argument here, okay? And then we are going to do data equals and put the name of the data frame to which both of these variables, post-test and pretest, belong, which is the train D data frame that we read in and named at the beginning. Now, the fourth and last argument we're going to enter is paired equals true. So if you recall, or if you've looked at the independent samples t-test tutorial, you would put paired equals false equals for an independent samples t-test. But in this case, the data really are paired. For each person, the pretest and the post-test vectors, their scores are paired with one another, okay? So we're going to do paired equals true to specify we're running a paired samples t-test. Now the next step is let's click run. And so you get a nice lollipop visualization here, which shows the difference from the pretest to the post-test here. So you can see how much of a change people had, okay? And you can see where this is the lollipop portion of it. This is going to be the pretest. And so in this case, you can see this person actually got worse to the post-test, whereas most people got better from pretest to post-test. And you can also scroll back, and here's the shape of that distribution there, and you can see here's 0. And so our real question is this mean that's associated with this distribution of difference scores significantly different from 0 here, okay? And you can find the answer to that question here, but let's take a look at the outcome for this function. So let's quickly move through this. You'll see that description includes our descriptive statistics for that distribution of difference scores. And you'll see that we have n equals 25, meaning that we have 25 different people or cases in this instance. And we'll see that the mean is 19.64 and the standard deviation is 11.60. So 19.64 is the average of the difference scores. Okay, so you can kind of see that the mean is somewhere around here, right before this 20 mark on the x-axis here. Okay, so this is a positive difference here. So what this means is that on average, we see scores being, at least descriptively speaking, being higher than the mean, meaning that people increase from pre-test to post-test. But the question becomes, of course, is that a statistically significant increase? Should we treat that as statistically significantly different from zero? Okay, so we do have here a formal test of that normality assumption, that univariate normality assumption for the different score distribution here. So in other words, we're trying to find evidence statistically whether or not this appears to be a normal distribution of values. And so we use the Shapiro-Wilk normality test. And here's the test statistic here, but what we're really interested in is the p-value associated with that. And the null hypothesis is that the distribution is normal. And so in this case, because we see that the p-value is greater than or equal to 0.05, we fail to reject that null hypothesis that the normal distribution of the difference scores is, or that the distribution of the difference scores is normal. And so in other words, we don't have any evidence to suggest otherwise that this is a non-normal distribution. In other words, we can say that we've with some confidence that we've met that statistical assumption that these difference scores are normally distributed in the underlying population, okay? And so if this were below 0.05, this p-value here, then we would reject the null hypothesis that this is a normal distribution. And in that case, we'd probably say there's some evidence that this is not normally distributed, and therefore this paired samples t-test might not be an appropriate inferential statistical analysis. Okay, so we have met this assumption. We did it visually earlier, and now we've done it using the Shapiro-Wilk normality test. So let's move on to inference now, which is the inferential statistic we're interested in. And so here, what we're really interested in this line that is the hypothesis test of the mean. And here you can see what we're testing the mean against is a value of 0. This is conventionally what we do, is we see whether or not statistically significantly different than 0, this mean of the difference scores. Now you could set this to something else too if you wanted to change this to, let's say, we're actually interested if it's different than 10 or something like that. So here we have the test statistic, the t-value, the degrees of freedom, which is just n minus 1, so the sample size minus 1, and then the p-value associated with that t-value, which is 0.00, so a very small p-value. Now this p-value is less than 0.05, which would be our conventional alpha level two-tailed, and so therefore we would reject the null hypothesis that this mean is equal to 0, okay? So in other words, we are concluding that, in fact, there is this mean that we saw above of 19.64, which means this is the average difference score here, or in this case, you can think of the average change score, is significantly greater than 0. So here we're concluding that this is statistically significantly different from 0. Okay, so we can treat that mean of 19.64 as significantly different from 0 because this p-value is less than 0.05 here. Okay. Now, because we found that this was a statistically significant difference between our mean and 0, then we would proceed forward and interpret the practical significance by going to effect size. Now, if we did not find a statistically significant difference, meaning the p-value was equal to 0.05 or greater than 0.05, which is our conventional two-tailed alpha level, then we would stop here and conclude that no, the difference scores do not significantly different on average, deviate on average from 0. So let's move down to the effect size now. Again, this can be used as an indicator of practical significance. We see Cohen's d, which is a standardized distance or standardized mean difference here, is 1.69. Now, conventional cutoffs or rule of thumb for Cohen is that 0.2 is small, Cohen's d of 0.5 is medium, and a Cohen's d of 0.8 would be large. Well, this is almost double 0.8, or more than double, it's 1.69, so this would be a very large difference here. So this means that on average, we see a large difference. This 19.64, which is the average difference from pre-test to post-test, is actually quite large. So this would, in a practical sense, be a quite meaningful difference. Now we're still left with the question is, did the training in this case cause this difference, or is it just other natural or outside factors, or just natural maturation in the population? Well, that we can't answer with these data alone, but here we can at least say that we do see this increase from pre-test to post-test that is statistically significant, and practically it's a pretty large effect. Okay? All right, so what if you would like to plot this finding? You've got this statistically significant finding. It also seems to be practically significant as well, something we should care about. Well, let's create a bar chart of the pretest and post-test means here, okay? Just as a way to visualize and see, okay, can we see that those means are different from one another? And in this case, we should see visually a difference depending on how we scale it, because we do have statistical significance and practical significance here. Well, we need to prep our data first. And so bear with me here, because the first thing that we need to do is create a vector of means that represent our pre-test mean and our post-test mean and put them together into a vector of values. Now I'm going to call this pre-post underscore means is what I'm going to name this vector of values. And I'll use the left-handed arrow to say I'm naming it. Now I'm going to use the C function, which stands for combine, which is from base R. And I'm going to use as the first argument, the mean function from base R to apply the mean calculation to the data frame train D, and specifically our pretest variable. Okay, so I'm using that $ again to say this pretest variable belongs to the train D data frame. And then after that first mean function here, I'll add a comma. And the second mean function we're going to specify is let's calculate the mean of, again, it's from the train D data frame, $ to connect it, that post-test variable, okay? So here we have pretest, post-test. We're going to create a vector of two means, one for the pretest, one for the post-test. Okay, so let's click run. And so now you'll see that you have this new object here called pre-post, and this is a vector of means. If you highlight it and click run, you'll see in your console here we have the two means, 52.72 and 72.36. So mean of the pretest, mean of the post-test scores. Okay. Now, we don't have labels for these yet. So we actually are going to ultimately create a data frame here. So how do we create labels? We need to create another vector that's going to contain the variable label or the variable names. Okay. And so let's call this one mean names. Okay. Actually, I'll call it mean underscore names here to keep that naming convention similar. So this is arbitrary, but this is what I'm naming it. And using that C function again, now I'm just going to type in quotation marks what I want to call the first variable. And this is what will appear in the chart so you can be more descriptive here. So I'm going to do pre-test in this format with a hyphen. As a second argument, I'm going to, in quotation marks, do post-test. Okay, so these are the mean names here that I've called them. Okay, so let's go ahead and run that. And if you just run this vector of variable names here, okay, so mean names, highlight and click run, you'll see, okay, we have pre-test, post-test. Now, how do we put these together? Well, to put these together, we need to actually create a data frame, okay? And so let's create a new data frame object that we'll use as input into our bar chart function from lessR subsequently. So we'll do mean, let's call it means underscore df here. Okay, you could call it whatever you want. And again, we use the left-handed arrow to say this is what we're going to name this new data frame. And we'll use the data.frame function from base R, okay? And we are going to type in first the mean names. So this is the name of the vector of variable names first, then comma, and then our second argument we're going to enter is that pre-post means vector of actual numeric values here that correspond with these mean names. And make sure that you get these exactly right. It might be better to copy and paste these to make sure they're exactly the same. And then click run. Okay, and now you'll notice in your global environment, you have now a data frame, a new data frame called means underscore df that we just created here. So you click on it. And so you'll see you have a very small, simple data frame here where we have mean names, pre-test, post-test, and we also have the values that are associated with those. Okay. This means that now we can enter this, use this data frame and these two variables in our bar chart function. So the bar chart function is going to come from the lessR package. And before we do that, one thing I'll mention that's sometimes helpful to do is because this data frame here has mean underscore names and pre-post means as the name of the vectors of interest or the variables of interest. And notice we also, because we created a data frame out of those, we also have just standalone vectors of these same values with the exact same names. It's sometimes a good idea to remove these vectors from your data frame so you don't get confused later on. So we'll use the remove function from base R. And for the first one, we'll copy the name of this vector, which is prepost underscore means. Oops. Copy. And then paste into the remove parentheses as a sole argument. Click run. Now you notice that one disappears from your global environment here. And let's do the same thing. I'm going to copy this. And let's now remove the mean underscore names vector that we created. Okay. And click run. And you'll see that's gone now. Okay. All right, so now we won't get as confused, hopefully, and which thing that we're referencing here. Okay, you didn't need to do this, but I think it just simplifies things and makes it clearer what we're actually doing here. Okay, so the first thing that you're going to enter in your bar chart function is the mean names variable from this means underscore data frame here. So we're entering this information here. Means name, or mean names rather, and then comma. Your second argument is going to be the pre-post means variable. Okay, so this is from that means df data frame as well. And then we specify that these two variables are from that means df data frame. Okay, and so here we're going to type in data equals and means underscore df here to specify these come from that means df data frame. Okay. Now we can click and run it like this. Let's see what the visualization looks like, this bar chart, as is. Okay, so you'll see the two means here. We've got the post-test and the pre-test means here. This actually looks pretty good, but I think we can do better with the x-axis and the y-axis labels. So let's go back up here and add an additional argument. I'm going to hit enter to go down to the next line here in the function. You don't need to do that necessarily. And I'll do xlab equals argument, and then in quotation marks, let's specify what we want to call the replace mean underscore names with here on the x-axis. Well, I think pre-test, post-test, let's just call this test time or test occasion, we could call it. And then after the quotation marks, I'll do another comma and I'll hit another enter here, and I'll do ylab equals. And so what do I want to call the y-axis here? Well, let's just say average score. That's what I'll call it, average score. Okay, and now let's highlight this, or you can put your cursor here, but I'll just be clear. I'll highlight all three lines and update this, and now we have test time, average score. So this is a pretty good data visualization right here. Now you could precede this with the style function if you wanted to do some additional stylistic things like remove grid lines, change the colors, and things like that. And you can use, if you just run this line here, question mark in front of the style function and click run, it'll, in your help window, the style function will appear and you can learn what all the different arguments are. And then after you're done, you would just add style with no arguments here and run that to turn off the style so that it resets it to the defaults if that's what you want to do. Okay. All right, well, this wraps up doing a paired samples t-test in R. Again, this just shows how to do it using the t-test function from lessR. You could use the t.test function from baseR, but you would also need to use, for the Shapiro-Wilk test, you would need to grab that from baseR, a corresponding function there, as well as if you want to calculate the effect size, that would be a separate step when you use the t.test function from baseR. So the t-test function from lessR does a great job doing a paired samples t-test, and it gives you a lot of things that are ready to go, including that test of the statistical assumption. So this wraps up the tutorial on paired samples t-test in R.